So my name is Shane Kennedy. I'm the Deputy Director for Science here at the European Spallation Source. I'm also head of the Neutron Scattering Systems Project Division. And in that capacity, I'm responsible for building the neutron scattering instruments for the European Spallation Source here. The way we're structured, we have major projects in civil works, in accelerator works, in target systems, and in integration of systems, and then neutron scattering systems. So my expertise is not really in accelerators. What brought me here is the opportunity to be involved in bringing to Europe and to the world the next generation neutron science source. And my expertise, very much having come from a nuclear reactor background, is in steering neutrons into scientific applications. So I can give you some sense of what we're doing in terms of accelerator physics, but mostly I'll be talking about the neutron scattering. And with that, I just wanted to start with a brief history of neutron science, of the development of sources for neutron science. And I don't really know whether this is familiar territory to you or not, so I'll just take my time to go through. I start with the discovery of the neutron by James Chadwick in 1932. And you can see soon after that, the first sources were all radioactive sources at first, and then finally synchrotrons came into play. This is through the 1930s and 40s. It wasn't until 1942 that the first sustained fission reaction took place, and that was the CP1. So the lead of that project was Enrico Fermi. It was based in Argonne National Lab in Illinois. And from there, very much the early development was through the war years, in fact, through the US. So the first 10, I think the next two, CP2 and X10, that was at Oak Ridge, I believe. And then I think perhaps the next one was in Canada. So very much in North America. But then there was a proliferation of sources around the world after the war years, neutron sources, and they were mostly multi-purpose research reactors. So neutron science was just one of those things. But you can see here, if I look at the blue curves from CP1 in 1942 up through the next few decades, more and more interest was shown and investment was made in fission reactors, in research reactors, to serve neutron science. And that was really the massive growth for the industry. But by the time we got to the early 1970s, it was pretty clear once the two biggest reactors, one at Oak Ridge and one at Brookhaven in the US, and soon after the Institut Larry Langevin in France came online, it became clear that really we had reached the limit of neutron flux that could be produced at a fission source.
I'm very sorry. I'm sorry. We can only see your title slide, unfortunately.
Yes.
Sorry.
Aha. Okay. Let me go back. According to my screen, I should still be sharing, but let me go back and restart the share. I'm sorry about that. Can you see it now?
Yeah, it's perfect. Thank you.
Let me just check that it's moving. I'll go back to the first slide.
Yes, it's moving now.
Okay, but now it's only going in one direction. That's not what I want. Okay, I'm sorry. I've just talked through all this without you seeing what I'm referring to. I won't go back really, but I just mentioned, I guess, with the first nuclear fission reactor in 1942 in America, CP1, we could see this growth of neutron flux. And this is what really served neutron science. It was really established in the next few decades that these sorts of fluxes were very useful for studies of materials physics, materials chemistry, material science, and so forth. But as I was saying, by the time we got to the late 60s and early 70s, we really reached the limit of a neutron flux that could be produced at a fission source. So fortunately, in parallel with that, starting in the 1970s, there was some development of spallation neutron sources. And the first ones here, you see the Tohoku LINAC and XingP, also at Argonne. And the first real pulse sources came online about the same time. One was at KENS in Tsukuba in Japan, and the other one was at IPNS in Argonne National Labs. And that showed a great deal of promise. And it's a very different method. Spallation neutron sources and fission sources are fundamentally different in the sense that these LINAC sources or these spallation sources are pulse neutron sources. But you can see here over time, the spallation sources continue to increase in performance. So you can see here with ISIS, and more recently with the spallation neutron source at Oak Ridge in America and the J-Park at Tokai in Japan. You can see these spallation sources now. Finally, we have peak fluxes that are well in excess of the fluxes that you can achieve at reactor sources. Nonetheless, the reactor sources have continued to grow, and second generation sources have been built in a number of countries. And you can see there's a number of modern ones here, most particularly the FRM2 in Garching in Germany, the Opal reactor in Sydney, and most recently 2 reactors in China. But the future of neutron science, we think, rests with spallation sources. And so the idea behind the ESS is to provide the next generation source and to provide unprecedented beam power, neutron fluxes to serve the science of the future. So as it stands today, I just have here in the bottom of the screen, you can see the top science producing neutron sources around the world. If I take it by region, you can see there are still some in Europe, ILL, ISIS, MLZ, and SynQ in Paul Scherrer. In fact, I should remove Orphée. That's since closed down. That's in Saclay. In America, there are 3, 2 at Oak Ridge, the SNS in the Haifa, and the NIST facility in Gaithersburg. And then the Asia-Oceania region, Opal, which is a reactor source, and Hanaro, which is a reactor source, and the J-Park, the spallation source at Tokai. So the principle for ESS is to provide for Europe, as I say, the next generation, an unprecedented power for neutron science. And let me just explain what I mean by neutron science here. What has emerged over 7 decades now of neutron scattering is that the neutrons can provide unique information at the atomic and molecular level on a range of materials that spans right through the hard sciences, through engineering and applied sciences, and right through to soft matter studies, polymer chemistry, and life sciences, and even medical systems. So this is why these sources have proliferated, and this is why it was seen to be worthwhile investing in next generation multinational source here in Europe. It's shown in this slide, neutron scattering, but in fact, neutron imaging has also come in leaps and bounds. And I've got an illustration on the next slide just to, I think, to illustrate why neutron science has found its niche. And it's because of the unique, the nature of the interaction between the neutron and the nucleus, and in fact, the magnetism related to atoms. So here I have an image here, a very common one, this simple coffee percolator. And what you can see in this is actually a movie taken at the Paul Scherrer Institute on the neutron source there. Yes, it's going here. And this is making a cup of coffee. And what you can see is the aluminium is very light. The plastics in the cap and the handle of the cup are very heavy, but the coffee itself, the coffee grains, the rubber seal, and the water itself all show very darkly on this image. And I guess the point is that the neutrons here, they are very sensitive to the light atoms, and therefore quite distinctly different to electrons and X-rays in the contrast that they bring. You don't get from this But it is also true that the neutron's magnetic moment also provides a unique opportunity for studies of magnetic materials and magnetic interactions right down to the atomic and subatomic level. So let me talk about the ESS, why it is that the ESS is predicted to be just so powerful. And it brings together a number of key factors, the ESS. So the first is the LINAC. So this LINAC is something like 700, the tunnel itself is over 700 meters long. This provides us with a proton source, a pulse proton source that is has unprecedented power. 5 megawatts is the design power of this source. It also has a target which is unique. The target station, it has this array of beams feeding on either side of the source with up to 42 extraction points at 2 heights. And we can actually host here, without any major upgrade in the facility, we can host over 30 instruments, high performance instruments, which means we really can look at the optimized instruments for a broad range of scientific application. And the next is in the nature of the moderation of the neutrons. You can see here this image shows you here, this schematic shows you here. We actually, of course, produce, when we have such high energy protons, we produce neutrons at extremely high energy. We moderate the energy or reduce the energy to the levels from the GeV levels down to milli-electron volt and even micro-electron volt energy levels by moderating here. And here we have this complex moderator system, which is actually unprecedented, where we can produce both thermal neutrons and cold neutrons, and we can extract them both in parallel, if you like, to the same experiment station. And that compact source, what we call bispectral moderator source, is a feature that really adds to the competitive edge of the ESS. And finally, it's the nature of the accelerator itself. It's the first long-pulsed neutron spallation source. And so, I mean, I have it illustrated here, but I go on to the next slide and show it a little bit more detail. And here, I'm giving you a comparison of the pulsed source of ESS to the pulse sources of the existing high-performance spallation sources. So the first one here I show is ISIS, which is at the UK, at the Rutherford Appleton Laboratory, the SNS at the Oak Ridge Laboratories in the US, and JPark. And if you look at the pulse here, the pulse width, for starters, of the ESS, the long pulse, it exceeds by a huge margin the pulse widths of these other sources. So it's a long pulse source, but it's also a very intense pulse. And effectively, the neutron, effective neutron power is roughly equivalent to the area under this curve. So the design for ESS, the current design, when operating at 5 megawatts, you see the line here. I hope you can all see the arrow. What we're building for day 1 operation, or within scope up to 2025, is 2 megawatts beam power. And that's this red line here. You can see the lower curve. So what we will have initially is 2 megawatt power, extremely high brightness and long pulse times. And then there's a capacity with addition of further accelerator modules to go up to 5 megawatt power. And everything's designed to do that, including all the safety systems. So by comparison, you can see that this spallation source will have much more brightness, very much higher brightness than any other source. Also, for comparison, I show you here, the highest performance reactor source in the world is the ILL, and that's been the case since 1972 when it first went to full power at 57 megawatts thermal. So this is a continuous source, not a pulse source, but the time average of equivalent for these sources. You can see the comparison here. The ESS will also by far and away outperform, in terms of neutron brightness, it will by far and away outperform the most powerful reactor source in the world. So it's a good, it should be an excellent replacement because the ILL is already 50 years old, and it can't be expected to go all that much longer into the future. So the ESS will be the place of choice for Europeans for high performance neutron science. So a few words on who's involved in the ESS. You can see here the founding member states. So there are the three Scandinavian countries, Sweden, Denmark, and Norway. And then you can see the participating European partners, a total of 13. And the total project funding is you can see here in 2013 euros, 1.84 billion euros, with the host countries putting up nearly half of that, and mostly in the form of cash, and the host countries being Sweden and Denmark, and the rest of the countries putting up just over half, mostly in the form of in-kind deliverables. And so the in-kind model applies here. It's a very important part of what we do here, is that we work in-kind with our partners, with all the neutron science labs around the member countries, using their expertise to get this source built. So here's the key in-kind partners. There are actually more than this, but the major ones here you can see dotted around the member states. And we have here, we're very fortunate, I think, we have all the best of the labs that have expertise in related in neutron systems and in also accelerator-based systems, delivery systems. We have a workforce now. We continue to grow. We've been growing since 10 years now, effectively, since we really started as an organization. And the workforce, we have over 500 employees and from over 56 nationalities. So we really are a global organization, and we do enjoy the benefits of that because we have this really amazing mix of skills and diversity in culture and in experience from various places where we have all come from around the world. So this is just a brief overview of the neutron instruments that we have. So although we have the capacity for more than 30 instruments, what we're doing in the project up until the end of 2025 is we're putting together 15 instruments. So roughly half of the capacity we'll fill with these first 15 instruments. And this is my own responsibility to make sure these all get built and operate at a very high performance. And you can see the spread here. So here's the protons come in from the bottom of the beam here and hit the target through the moderator and out into the instruments here. You can see here we've got names for these 15 instruments. And also what I've done here is I've labeled here the main partners who are leading in the construction. And the point here is that for the neutron instruments, we very much depend on the expertise around Europe in neutron instrumentation from existing neutron sources from our partners, for example, at the Paul Scherrer Institute or at ISIS, in Jülich, and ESS Bilbao, the Technical University of Munich, and the RLB in Saclay, and so on. So all these partners are working with us and actually leading in these instrument constructions to bring these instruments into fruition and ready as soon as the new, or in some cases, ready as soon as the neutrons are produced from the source point. So I go on now, and I'm just going to give you some status, I guess, of where we are today. So this is a very recent aerial photograph of the site. You can see here in the top right of the screen, underneath this berm is in a tunnel is the LINAC. That's feeding up here. There's a dogleg bend to bring the proton beam up and insert it into the target station, which is here under this where my arrow is. And you can see there pointing to that the fan of buildings where the long neutron instruments are housed, and some of the shorter neutron instruments will be here under this building just adjacent to the target station. We're also now progressing quite well to build permanent offices and permanent workshops and laboratories. At the moment, most of us, and I'm in fact myself, sitting over here in one of these temporary buildings, but as we move forward, we will all vacate this area and there'll be enough permanent space for the staff here. So we're 72% complete. Now I give you a slightly closer aerial view, which shows you a bit of a better view. This is where the beam, the dogleg is to bring the proton beam up onto the target station down under here. This is one of the near areas where some of the spectrometers are. And as I say, others will be further out here. There's so many challenges that come when you go to produce a source like this, a neutron facility like this, with unique characteristics. And some of it is just the scale of this. There's no existing source that has such long beam lines here. The reason they're so long is it relates to the nature of the source itself. There's a good reason in terms of performance, but what it means is that we actually have on each of these instruments, there are 8 will be housed under here. The path length is in excess of 160 meters from the target out to the instrument station. So we've had good progress, apart from what you can see above ground. We've had good progress in the tunnel, and I just have some recent pictures of work going on at the RF systems down in the tunnel. But I should say the ion source is already installed, and there's been a lot of progress on the normal conducting linac and in the cryo system for the superconducting linac system. So that well advanced on installation for the accelerator work. The target station itself, everything here is of course bespoke and very much in a prototype phase now. But here is pictures from Spain where the reflector vessel is being built, which will house the target, house the moderators, and facilitate extraction of all these neutron beams. You can see here the target wheel, the construction of the target wheel. This will be a target wheel with something like 35 elements, which rotates around at a speed of a few hertz. This will have arrays of tungsten elements around to produce the spallation from the interaction, from the impact of the high energy protons. You can see here some of the beam extraction port blocks also in construction. In terms of what we're doing to prepare for the instruments, you can see we have already prepared the work for the primary shielding. The shielding requirements for this source are massive, quite unprecedented. We had to do a great deal of work to ensure that we could build this safely and shield it in such a way to protect all the staff and also members of the public from the normal radiation, but also from various potential accidents that could occur. So we've done a lot of work here to prepare once the target is here, to prepare for the beam extraction. At the moment, we're just preparing to build this massive bunker, 11,000 ton heavy concrete bunker around this to provide the first level of shielding. And we're just getting into now building the instrument caves, the very heavy shielded instrument caves out in the long sector. A lot of key technologies we've had to develop for the first time here. So we have the largest, I think the heaviest choppers that have ever been designed and built. We're now in the prototyping phase. These are the T0 choppers, which will absorb the prompt pulse for the neutrons coming out from the source. Heavy shutter systems, which are up to 1.5 meters thick, also to isolate the beams when we want the beam off for maintenance or other purposes. And then we've got a whole range of high performance neutron chopper systems, disk chopper systems that are under development in order to make the most of the neutron source. And they're now well on the way through prototyping and into construction. And then we've also had to develop detector systems uniquely for the ESS. And I just mentioned this because I do believe in this conference that there is some interest in development of detector systems for radiation. So one of the challenges for the ESS was because of the very high flux and also because of the very high peak flux, the very high instantaneous flux. we needed to develop detectors could handle much higher rates than exist and at an affordable price. And the benchmark has been helium detectors in the past in neutron science, but it was determined here that this would not serve us in order to get the full performance and also to fit in with the cost envelope that we have. We need to develop our own detector system. So what we've come up with over 10 years now in development is a boron-based detectors, and we're just now moving into construction of the first of those for some of the instruments. So you can see here this one for one of our inelastic spectrometers we call C-SPEC. We'll have 18 modules of detector modules. They're nearly 4 meters high and each one 300 millimeters wide. They'll sit on the circumference of this big evacuated detector tank at a radius of 3.5 meters. And they will have voxels, so a three-dimensional system. They will have voxels of the order of just a few centimeters each in order to capture all the information coming off the experiment. We're just moving into production now, so we've moved from the development and now into our own ESS-based production team. And this will cost 4.3 million once it's built. And that's typical of the cost of a detector for one of these spectrometers. So we've set everything up. We have all the facilities in Linköping for magnetron sputtering coatings of high purity aluminum plates to build these arrays with the B4C. And we've also established an assembly workshop and staffed it here in Lund for the full production of these detector systems. So I just take a few moments. I see I'm really finished my time. Take a few minutes to talk about the timeline. So this is what I'm showing you here is the current schedule to bring us to the point where we will produce first neutron, so that's beam on target here. First science, when we actually will have done enough of the commissioning to show some exciting results off the early spectrometers, and when we would formally start the user program. So what you see here in the BOT, FS, and SOUP dates, that's our formal baseline schedule. But we're now dealing with a number of issues. That was set over 2 years ago. We're dealing with a number of issues, some related to delays in delivery of some key components, but also related to the COVID-19 pandemic, where we now are forecasting that the dates will move to some later point. So now what we're expecting is that we will be ready for beam on target in March of 2023. So it's about a 9-month shift from what you see here. And it's largely due to the critical path delays in the target part. The accelerator should be ready well before that, and the neutron scattering system should be ready a little before that date as well. But this is the line we're now working to. So with this in mind, we're putting together a very detailed plan for installation of the first instruments. So we expect that, by the time we get to beam on target, that's this date here, early in March of 2023, we expect that we will have the system all safe. We'll have the test beamline operating so that we can monitor directly what's coming off the source. We can compare that to all our predictions and our calculations. But we also expect that up to 6 of the instruments, or 6 of the 15 instruments, will be ready by that time to receive the beam. So in principle, those 6 instruments can go through their early commissioning right from the point of beam on target and all work to the point where they can start to do some preliminary science before the end of 2024. Before the end of 2023. So our current target is to get to beam on target in March of 2023 and to start producing science later that year, and then to move on to a formal full user program in the following year in 2024. And when we do that, we will have an open access will be the dominant method. So this is peer review access. It's only scientific merit that will be judged in order for users to come and use the facility. We will have a very big team of staff to support all the experiments. And we expect that over 200 days a year, we'll be operating a full service user program. So with that, I'll end the talk. Try to leave a few minutes at least for questions if there are any. Thank you.
Okay. I just found first one question in the chat. It's from YouTube stream. What are your prospects on initial confinement fusion as a neutron sources? Would they in future train higher flux than spallation sources?
I just stopped to share. That's an interesting question, and I have to say I don't know the answer. I mean, I know there's the projections so far that I've seen that the spallation sources still have a way to go, but ESS won't be too far off the limit. So there may be some interest in that, but whether this fusion process is shows a promise, I'm really not qualified to answer.
I have myself one question more practical. And what proton energy you selected?
So the proton energy design is for proton energies up to 2 GeV. And in fact, at 5 megawatts of power, we assume we're at 2 GeV and 62 milliamps current. But we'll start the system at, I think we'll be starting the system at something like 500 MeV.
So as I remember, the maximal ratio, maximal exit of a neutron is about 1.8 GeV. So you are exactly the maximum to have the maximum exit, just the ratio for neutrons to the protons.
Correct. Yes.
Okay. Other questions? I do not see other questions. Really, I have a lot of the questions, but they should require a very long time because you have, for example, 6 instruments, but it's very interesting. What is the difference, for example, between these instruments?
So I can say very broadly that across the 15 instruments, we want to cover the current interest in condensed matter physics, in material science, in engineering physics, in solid state chemistry, across the life sciences. And so it's about structure, atomic level structure. It's about the dynamics, structural dynamics at the atomic and molecular level. It's also about all things to do with the magnetic interaction. So that's magnetism and superconductivity. And then there's also, in some cases, an optimization in what we call reflectometry to study surfaces and interfaces. So to look at particular sorts of morphologies and to understand at the atomic level. But the overriding principle for neutron scattering and where neutron science has gone is that there's an enormous capacity with neutron scattering to study materials, whatever it may be, in situ or in operando. So these days, most of the experiments are done at extreme temperatures or extreme magnetic or electric fields or extreme pressures. And it's very much the case that people are looking to understand in real life systems under the circumstances that are of most interest for science. I hope that gives some broad sense anyway of the breadth of what these sources do.
I'm sure it's impossible to answer totally for such a small time. Really, it's a pity for me that Russia isn't participating in the ESS. Some ideas was to participate, but finally, you see, there is no Russian participation. Okay, are there any other questions? Okay, if there is no any other questions, I want to thank Shane for brilliant talk, and for all others, I think we will meet in an hour for our next plenary session. So thank you very much for all.
Thank you, Vasily.